Hi everyone, welcome to the second lecture of the series on control of mechanical systems. In this lecture, we discuss the mathematical modeling of mechanical systems. Here is the overview. We start with a brief discussion on the mathematical modeling of mechanical systems. Then we move on to the time domain and frequency domain modeling. Mathematical models are used for describing the behavior of mechanical systems. Here by models, we mean some equations that describes the relationship between the physical variables of the mechanical systems. These relations will be usually in the form of differential equations, mostly ordinary differential equation, and it can be also partial differential equations. In this lecture series, we are considering examples of mechanical systems that are modeled using ordinary differential equations. And these ordinary differential equations can be represented either in time domain, which is in the form of linear or nonlinear state equations, or in frequency domain, which is in the form of an input-output model or transfer function. Let's start with the time domain modeling. We have the general form of the time domain model for linear system is in the form of equation number 1, in which x is the state vector, which is an n-dimensional vector, u is the control input vector, which is an m-dimensional vector, y is the output vector, which is a p-dimensional vector, a, b, and c are the system metrics, input metrics, and output metrics respectively. Here, each elements of the state vector are called as the state variables, and similarly for the control vector, we call it as the control variables, and the elements of the output vector are called as the output variables. Now for the nonlinear system, we can have the general form of the state equation as in equation number 2, in which x, u, and y are the state vector, input vector, and output vector respectively. F and h are nonlinear mapping, which represent the state and output equations. Here we can see that the linear system is a special case of the nonlinear system with some specific structure for the f and h. As an example of the linear system, we can consider a mass spring damper system as given in figure 1, in which m is the mass, k is the spring constant of the spring, p is the friction coefficient of the damper, f is the applied force, x is the displacement from the equilibrium position. Now for the mass spring damper, we have the dynamics can be represented as in equation 3 using the force balance relations, which are based on the Newton's laws of motion. Here we can see that the dynamics of the mass spring damper system is defined by a second order linear differential equation with the time as the independent variable. Now by choosing the state variable x1 equal to x, which is the displacement, x2 equal to x dot, which is the velocity, control input u is equal to f, the output variable y is equal to x1, we can represent the second order differential equation as two first order differential equations as shown here. Here by x dot we means dx by dt. x1 dot means dx1 by dt, which is basically dx by dt. This first equation comes from these two equations, and the second equation comes from rearranging the equation number 3, in which we have x2 dot is equal to x double dot, which is d square x by dt square, and it is equal to minus k by m times x minus b by m times x dot plus 1 by m times u. Now these two equations can be represented as in equation number 4, which is of the form of a general linear system, in which we have this term will become the A matrix, this will become the B matrix, and this term becomes the C matrix. Next, we consider a nonlinear system example in which we consider a simple pendulum as shown in figure 2. M is the mass of the pendulum, L is the length, theta is the angle from the equilibrium position, T is the applied torque, and we have for the simple pendulum the moment of inertia J will becomes ml square. And by using the torque balance relations, we can obtain the dynamics of the simple pendulum as in equation number 5. Here we have a term with sine of theta, which makes this differential equation nonlinear. Now by defining the control input u is equal to t, the state variable x1 equal to theta and x2 equal to theta dot, which is equal to omega, we can represent the second order differential equation as two first order differential equations. This results in the state equation of the simple pendulum as in equation number 17. Here due to this nonlinear term, we cannot represent this in the form of ax plus bu. Next, we move on to the frequency domain modeling. Frequency domain models are mostly used for linear systems, and it is usually represented as a transfer function which gives an input-output model of the system. Transfer function is basically the ratio of the Laplace transform of the output and input with zero initial conditions. In general, the transfer function g of s is a function of the complex frequency s, where s is equal to sigma plus j omega, in which sigma is the real part and j omega is the imaginary part. Now for the linear state equation given in equation number 9, if we take the Laplace transform and rearrange the terms, we get y of s equal to g of s into u of s, where y of s is the Laplace transform of the output, u of s is the Laplace transform of the input, and g of s is the transfer function which maps the input in frequency domain to the output. So this equation is in the form of a linear transformation, where g of s is the transfer function matrix, which is an m by p matrix. And we have the general form of the transfer function for LTI system as C into SA minus A inverse B. For the mass spring damper system, we have A, B, and C matrices as given in equation number 12, using which we can derive the transfer function for the mass spring damper system as in equation number 13, in which we obtain the final expression as 1 by m into s square plus d by m s plus k by m. That completes this lecture. Thanks for listening.